In the last video, we talked about how we could model the electrostatic interaction between a point charge and an infinite conducting plane with image charges. In this video, we'll apply what we learned to solve an actual Olympiad problem. And this was taken from the 2000 Boston area undergraduate physics competition. Problem 2 states that there are two conducting infinite half planes meeting at a right angle. We have a charge Q that is brought in from rest at infinity to a position at rest a distance d away from each plane. So let's call this positive Q, and let's say it's a distance d away from the two planes. What is the work N to bring about this change? Now, before we solve this problem, let us first introduce the image charges, because as we know, the induced charges on this conductor would cause the electric field lines to be perpendicular to it. We can solve this problem and mimic those behaviors by having an image charge here. Also a distance d away, but with a charge of negative q. This way, if we place a test particle at the conductor, the electrostatic field, or the force there, would point downwards for a positive charge. But there's also a second conductor that we need to worry about. And again, similarly, we can place another charge of negative q, also a distance d away. However, the problem that you might see is that by introducing this new charge, the field at this point will no longer be pointing perpendicular to the conductor. Instead, it would be slanted a bit. And similarly, if we place a test charge here, it won't be exactly perpendicular to the conductor either. And to solve this problem, what we can do is reflect the two charges across this imaginary conductor border. And the reason this works is if we have a plus q here, then these two effects perfectly cancel out. The electric field that this point experiences from the rightmost two charges will be pointing down, and the electric field from the left two charges would be pointing up. They would face in the same, in different directions, but it would be purely vertical, and it would result in a net vertical field. And the same thing on the vertical plane. So as a result, we are able to mimic this behavior exactly, and we can start to solve this problem. A asks us what would be the work needed to bring about this change. Now, the work N would just be equal to the change in energy. So we have U final minus U initial, and let's call Ui equals 0, because at infinity, the energy of the total system is exactly 0. So now this problem just becomes, what is the potential energy of these four charges? The naive way to do this would to just be individually counting up the for electrostatic potential between these four charges. And since we have 6 pairs of two charges, we can just write it like this. We have 4 pairs of interactions which act adjacent to each other. So we have 4 times negative kq squared, and it's negative because the signs of adjacent charges are opposite, and then a distance 2d. So just to make it clear, that's 2d, and that's also 2d. The 4 charges form a square. But there's also 2 interactions diagonally. So let's add 2 times positive kq squared, because the charges are equal to each other, and the distance here is given by Pythagorean's theorem to be 2d squared plus 2d squared. Take the square root of that, and we get 2 root 2d. we can simplify this by factoring out kq squared over d to get negative 2 plus 1 over root 2. However, this sort of thing is incorrect, because what we've done here is pretended the charges actually exist in these physical spaces. In fact, they don't exist there. And that's why image charges is just a problem-solving tool for us to mimic the field around this conductor, but we can't actually treat it like these charges are actually there. But don't worry, there's an easy way to fix this, because we can recognize that the energy of an electric field is just proportional to the square of the electric field. And the electric field is only available between the charge and the conductor and this quadrant. And as a result, the potential energy of this setup is actually reduced by 25%. There is no, in these three quadrants, there is no electrostatic potential energy stored in the field. So we multiply this by 1 over 4, multiply this by 1 over 4 to get kq squared over d of negative 1 over 2 plus 1 over 4 root 2. Now it makes sense that this answer is negative because there's going to be an electrostatic attraction between the two planes and the charge. So in order to bring this from infinity to its location now very slowly, we need to produce force in the opposite direction of motion. Now for part B. Part B asks, while the charge q is a distance d from each plane, the planes are changed from conducting to insulating. That is, the charges on them are no longer free to move. The charge q is then brought back to infinity. What is the work done about this? So this is a similar problem, but in this case, these three charges are already here. And they will continue to be here because the charge distribution of the conducting plates can no longer move. So we have workout is equal to the change in energy equals UF minus UI, but this time UF is going to be 0, so we're just going to be left with the negative of the initial potential energy. And notice how we set UF to be equal to 0. This technically isn't exactly true because there will be an electrostatic interaction between the two plates, since they are insulators and can no longer move to ensure that they are at an equipotential surface. So instead, we've only looked at the potential energy of our particle plus q at the top right corner here. Its potential energy at infinity is going to be 0. So we only want to care about the electrostatic interactions that it is involved in. So that it only interacts with 3 other test particles. So we can say that UI is equal to 2 times negative kq squared over 2d plus 1 diagonal interaction of kq squared over 2 root 2 times d, which gives us, we can factor out the k cubed squared over d, and we get -1 plus 1 over 2 root 2. And we have work out is going to be the negative of this, or k cubed squared over d of 1 minus 1 over 2 root 2. That's the answer to part B. Now for part C. What is the potential energy of the system of charges on the insulating planes? Now, to do this problem, we just have to recognize that we have constructed this in 2 different steps. The first step is that we took a charge from infinity and moved it to where it is shown. And then we locked it in place, and then we moved it back. We locked the charge distribution in place, we moved it back to infinity. So the resulting potential energy in the system is just going to be the answer to part C. And we can get that by just adding in the 2 works that we've calculated in part A and part B. So we have the potential energy is going to be equal to work in plus work out, which is going to be equal to k cubed squared over d of -1 over 2 plus 1 over 4 root 2 plus 1 minus 1 over 2 root 2. And doing some simple algebra, we can reduce this to 1 over 2. We can times 2 on both sides, and that would give us -1 over 4 root 2 as the final potential energy of the 2 conducting planes. And there we have it. The 2000 Boston area undergraduate physics competition question 2.